Welcome to Sri Learning Academy. Let's simplify SRTF scheduling algorithm, also known as Preemptive SJF. Imagine a situation where your system is handling multiple processes and suddenly a very short job arrives, but the CPU is busy executing a longer one. Now, here's the question that changes everything. Should the system wait for the long process to finish, or should it pause it and quickly complete the shorter one first? That single decision leads us into one of the most practical and intelligent scheduling techniques called SRTF, or shortest remaining time first. SRTF is basically the preemptive version of the shortest job first algorithm. You already have an idea of SJF, where the process with the smallest burst time gets executed first. But SJF had a limitation. Once the process started running, it would continue until completion, even if a shorter process arrived in between. SRTF improves this by allowing interruption. The CPU always looks for the process with the smallest remaining execution time, not just the smallest total time. And if a new process arrives with a shorter remaining time than the currently running process, the OS immediately switches to it. This switching is what we earlier referred to as preemption, and it connects directly to concepts discussed in scheduling and context switching. To understand this better, imagine a real life scenario. Suppose you are at a printing shop and one person gives a 50-page document to print. The printer starts working on it. After a few seconds, another person comes with just a 2-page document. In a normal SGF like situation, the printer would continue 50 pages first. But in SRTF, the printer pauses the large job, prints the 2 pages quickly, and then resumes the longer task. This way, smaller tasks are completed faster, improving overall responsiveness. Let's take a simple example to see how this works step by step. Consider three processes. Process P1 arrives at time 0 with a burst time of 8 units. Process P2 arrives at time 1 with a burst time of 4 units. Process P3 arrives at time 2 with a burst time of 2 units. Now, at time 0, only P1 is available, so it starts executing. But at time 1, P2 arrives and its burst time of 4 is less than the remaining time of P1, which is now 7. So the system pauses P1 and starts P2. Then at time 2, P3 arrives with a burst time of 2, which is smaller than the remaining time of P2. So again, the system preempts P2 and runs P3. Once P3 finishes, the system chooses the next shortest remaining job, which would be P2, and finally P1. If you observe closely, the CPU is constantly making decisions based on the remaining time, not the original burst time. This makes SRTF highly dynamic. It reacts to every new arrival and adjusts accordingly. This behavior makes it one of the most optimal algorithms when it comes to minimizing average waiting time. Now let's break down how the scheduling actually progresses in a structured way. The operating system reevaluates the scheduling decision whenever a new process arrives in the ready queue or when the current process finishes its execution. If a new process arrives, it compares its burst time with the remaining time of the currently running process. If the new process is shorter, a context switch happens. Otherwise, the current process continues. This constant checking might sound heavy, but it ensures better efficiency overall. Let's extend the example slightly to understand waiting time and turnaround time. Suppose we track how long each process waits before completing. You will notice that shorter processes like P3 get completed very quickly, almost immediately after arrival. This reduces their waiting time significantly. However, longer processes like P1 may get interrupted multiple times, increasing their waiting time. This introduces an important trade-off. While SRTF improves average waiting time, it may not be fair to longer processes. This brings us to one of the key challenges of SRTF, which is starvation. Since the algorithm always prefers shorter jobs, a long process might keep getting postponed if shorter processes keep arriving. Imagine a system where small tasks keep coming continuously. A large task might never get CPU time. This is similar to what we discussed earlier in scheduling problems, where fairness becomes an issue. Another important point to understand is the overhead of context switching. Every time the CPU switches from one process to another, it needs to save the current state and load the new one. This is not free. It takes time and system resources. In SRTF, since preemption can happen frequently, the number of context switches can increase significantly. This can slightly reduce the overall efficiency if not managed properly. Despite these challenges, SRTF is still highly valued for its performance because it achieves the lowest possible average waiting time among scheduling algorithms, at least in theory. The main difficulty lies in knowing the exact burst time of a process beforehand, which is rarely practical. Systems may try to estimate this using past execution patterns, but these predictions are not always accurate. Because of this limitation, SRTF is often considered an ideal or benchmark approach rather than something directly implemented in real world systems. At its core, SRTF prioritizes efficiency and quick response over fairness. Short processes get completed very quickly, but longer ones may keep getting delayed, especially if new short jobs continue to arrive. This risk of starvation makes it less suitable for general purpose systems where balanced performance is important. In such cases, algorithms like round robin or priority scheduling are preferred as they ensure that all processes get a fair share of CPU time. So, when you think about SRTF, remember this simple idea. The CPU is always asking one question at every moment: which process can finish the fastest from here? And based on that, it keeps adjusting its decision dynamically. This ability to adapt in real time is what makes SRTF powerful, but also slightly complex to implement. As we move forward, you will notice how different scheduling algorithms try to balance efficiency, fairness, and responsiveness. SRTF leans heavily toward efficiency, and understanding this behavior will help you compare it with algorithms like round robin and priority scheduling in the upcoming topics. That is it for this video. See you in the next one.